right, so these two came up with the modern interpretation of the black hole theory in 1960s, which eventually evolved. All right, so here's how the modern interpretation looks.
If star contracts, its gravity becomes so strong that light can no longer escape. The region from which nothing can escape is called a black hole, and its boundary is called the event horizon. One might say of the event horizon what Dante said of the entrance to hell. Abandon all hope, ye who enter here.
All right, so the modern theory is visual. All right, let me check to see how well this works. All right, so the modern theory is visual. I gotta try this. This is weird. All right, so what looks like an S is gonna have an opening in the middle. Opening in the middle is gonna be smaller than the smallest atom in your body. This is known as a singularity. Center of a black hole is known as a singularity. All right, this shape that you're looking at, that S-looking shape, if you add one more dimension to it, it's gonna look like a cone. All right, so this is the shape of something called the space-time continuum. This is from Einstein's theory of general relativity. Space-time continuum. All right, so which gets curved or warped to the shape. This is known as the boundary of a black hole, otherwise known as the event horizon. All right, so this is the event horizon. It's so named because once you get past that point, the gravitational pull on the inside is simply so strong that even light won't be able to escape from it. All right, so that's the boundary of an event horizon. That's the border. If you get past beyond that point, that's it. There's no return. All right, so this thing that's composed of a singularity and event horizon is known as a black hole. Now, the size of the event horizon depends on the amount of mass which is squeezed at the center, or right at the center. The mass, according to the original theory, is going to get squeezed. You could possibly turn into energy at that point. Opening at the center is going to be smaller than the smallest atom in your body, so the mass is going to accumulate. The more mass you have at the center, the larger the radius of the event horizon is going to become. So the size of the event horizon depends on the amount of mass squeezed at the center. So this thing could be microscopic in size, or it could be literally light years across. All right, so depending upon the amount of mass squeezed at the center. This is the theory from 1960s. This is the original theory from 1960s.
But out here on the high desert of New Mexico, they found that black holes do exist outside of equations.
So how do you look for something which is black against the pitch darkness of the universe? We're going to be able to see something like that.
27 giant radio dish antennas, each 80 feet wide, are positioned over 13 miles to form a single huge radio telescope. They call this very large array of antennas the VLA, which stands for the Very Large Array of Antennas. James Moran is one of the world's foremost radio astronomers.
The VLA has had a tremendous impact over the last 15 years. It's very important because it has tremendous versatility. This technique of radio interferometers was developed after World War II, but this is the first really big array. Dust obscures light rays, but this instrument can penetrate that dust because radio waves go right through the dust, and we can see down to the core of things that can't be seen in optical astronomy, for example.
It turns out that a black hole can create radio signals as it sucks in matter. The signals can show up as a beam of microwaves, a microwave laser, or
maser. All right, so there are a number of ways you can actually detect black holes. Number one, when the mass is getting sucked into it. Masses are composed of charges. Accelerating charges radiate energy in the form of electromagnetic waves. So you end up getting the entire electromagnetic wave spectrum from these charges accelerated into the black hole. So you end up getting the entire spectrum, all the way from radio waves up to the gamma rays. And then you end up getting large concentrations. These guys are looking at the microwave as well as the radio wave frequency range from Earth because they're extremely large wavelengths. And large wavelengths can penetrate through clouds, so you can actually see through the clouds as well as dust in space. All right, so that's what these guys are using. Another way of doing it is related to the discussion that we were having in the beginning of the semester. All right, so how do you know that the gravity extends all the way out to the moon? You know that gravity extends all the way out to the moon, because if it didn't, what would happen? Straight line and constant speed, right? Yeah. Also, the fact that the moon is accelerating. So imagine that you see this star, and it's just doing this. It's literally, it's just moving in a circle, and there's a second star that you don't see. All right, so there's a void here that you don't see, and immediately you infer that there has to be a black hole generating tremendous amount of gravity in it, despite the fact that you cannot see it. All right, so the explanation that I came up with is a general explanation that most physicists will come up with. But
A microwave laser
there's a catch to it,
or
maser. All right.
Hubble has put some of astronomy's most treasured imaginings to the test. What Hubble did was look at the center of a galaxy where we suspected there might be a black hole. A black hole is an object that is very, very dense and very, very small. So dense and so tiny that the speed of escape from that object exceeds the speed of light. So nothing can get out of it. Everything just gets sucked into it and disappears from the universe. Black holes have been fantasy and science fiction for decades. And what Hubble has done now is it's shown us that black holes are scientific fact.
It's not quite bright. So why does it look so bright? So what happens to the objects is they are falling towards the event horizon. They start to accelerate, right? The accelerating charges emit radiation in the form of electromagnetic waves. In the visible portion of the spectrum, you will get light. So the objects falling into a black hole will glow just about the event horizon. This is what you end up getting. You end up getting a light show, in essence. Those of you guys who've taken astronomy regarding the spiral galaxies,
In the long history
you will see this. All right, what do you have at the center? All right, guys, don't say black hole immediately. Number one, you guys are looking at a spiral galaxy,
of
and you're looking at the negative of a spiral galaxy, negative image of a spiral
the
galaxy.
universe,
These dots that you're looking at, these are not stars, these are star clusters.
many stars
You may have million to billion stars within those
must
dots.
have burned up their nuclear fuel.
And notice that these stars and star clusters are moving with respect to a common origin at the center. All right, notice that the center contains nothing but a giant void, which happens to be the brightest
And
spot in the spiral galaxy that you're looking at.
collapsed in on themselves.
All right, so something at the center is generating tremendous amount of gravity, holding the spiral galaxy together. What that something is a giant black hole.
The number of black holes may be greater than the number of visible stars, which totals about 100,000 million in our galaxy alone. We also have evidence that there is a very large black hole at the center of our own galaxy.
So the next question is, how did they form?
when enough matter collects, gravity is strong enough to squish hydrogen atoms into helium atoms. This fusion releases enough energy to turn on a star. But gravity is also a star killer.
Stars are born, age, evolve, and eventually die, just like people. They have a regular life cycle. During the entire life of any star, there is this delicate balancing act, because gravity is always at work trying to crunch the star down into a small point, and the high internal pressures are trying to blow the star up and blow it apart. And for about 90% of the life of the star is in nearly perfect equilibrium. And it just sits there, burning away and producing radiation.
But when the fuel is gone and the fires go out, gravity is free to collapse the star. A medium-sized star like our sun will burn steadily for 10 billion years. Then, in a kind of cosmic spasm, it will puff up to engulf the inner planets before collapsing into one of those white dwarf stars. A star twice the mass of our sun would collapse even farther, ending up as a super-dense star the size of New York City, a neutron star. A teaspoonful of stuff from a neutron star would weigh 100 million tons. But what happens to a bigger star when its fires die down? Say a star 50 times the size of the sun. It may blow up as a supernova, leaving a neutron star, but then it keeps on shrinking to infinity, an infinitely small point with a gravity so powerful that not even light can escape.
So, how did they form? How many of you guys were able to catch that?
Just the collapse of a super big star.
Okay, so the dying star, under certain circumstances, if they have the proper size, can potentially turn into a black hole, right? Okay, so what caused the star to die, though? Okay, so
It ran out of fuel to keep its nuclear reaction going.
All right, both of you guys, I'm going to give you 5 points. So when they run out of nuclear fuel, okay, so what fuels a star, in essence?
Hydrogen?
All right, that's hydrogen, right? So what happens to hydrogen? Hydrogen fuses into helium, and then helium is going to fuse into something else, and this process is going to keep going on and on until everything is fused into something bigger and bigger. The biggest is usually iron at the core. So eventually, when the star runs out of hydrogen, it's going to run out of nuclear fuel. At that point, the core being extremely solid, the gravity becomes the dominant force, right? So it can potentially, according to the original theory, when mass goes to the center, it clogs it up. More massive the center is, the bigger the event horizon is going to be. So which means that the black hole gets more larger and larger.
When enough matter collects, gravity is strong enough to squish hydrogen atoms into helium atoms.
So the next question is,
a black hole can attract dust and gas in its neighborhood into a whirling disk of molecules.
Next question comes out of the discovery made in 1970s, 80s, and so on. Every single black hole that physicists discovered didn't quite look like the predicted black holes from 1960s. These are whirling black holes, twisting, spinning black holes. So because they were whirling and spinning, it was thought that this opening at the center would be large enough for something to go through.
Those molecules release great bursts of radio energy as they are drawn in. There seem to be black holes made not from single stars, but from whole clusters of stars. They have a mass 100 million times that of our sun. But these monsters are still infinitely small points, capable of gobbling up other stars. But where does the stuff that falls into a black hole go? Does it just fall out of the universe? Possibly. Or it may pop up somewhere else in space. If you'll excuse an indelicate metaphor, there may be white holes regurgitating matter eaten by black holes in another part of the universe, a wormhole in the fabric of space and time, allowing you to go from one location to another without crossing the space in between. Or it might go to another universe entirely. Astronomy's reigning theoretical genius, Stephen Hawking, proposed that the black holes in our universe might well give birth to other universes. In fact, there might be any number of universes, like bubbles in the bath.
All right, so we got a bunch of conjectures coming out of that. Early theory was that you have an event horizon. Obviously, you have the black hole, singularity at the center. You get your event horizon. So the mass would be falling into it, positive and negative charges. It's getting sucked into it. So what's going to happen is it's going to break down into its components. The opening at the center is going to be smaller than the smallest atom in your body. Everything is going to get quenched up and possibly turn into energy at that level. So what's the meaning of energy at that level? What does it mean? Mass turning into matter, turning into energy, and energy turning back into matter. All right, that's modern physics for you. All right, so given the fact that these black holes spin and whirl, which means that possibly the energy might leak out to the other side of a black hole. So the question is, what do you have on the other side of a black hole? All right, so the one thing that happens, the mass is going to go in, and nothing's coming out from this side, and then it turns into energy, and the energy is going to simply leak out from the other side. Guys, within the visible spectrum, you're going to end up getting light. And you're going to end up seeing light in its all colors. So which means that you're going to end up seeing white light. So what is a black hole from this side is going to become a white hole on the other side. That's what it means. All right, in essence, this is going to be a shortcut within the space-time continuum, if it's true, otherwise known as a wormhole. All right, so what do you have on the other side of a black hole? It may be a new universe starting, so it's a black hole from here, may become Big Bang on the other side. It may be starting a new baby universe. All right, so every single conjecture that you can come up with. Something that Stephen Hawking ended up covering in just about every single publication that he had, ever since 1980s. All right, so here's the catch though. What happens beyond the event horizon is unknowable. All right, you can come up with all the conjectures you can or you want. You're not going to be able to test any of the conjectures. And a lot of what goes on beyond the event horizon becomes science fiction as far as we're concerned. You can probe into it mathematically, and obviously math makes a lot of predictions, and you end up getting tons of infinities. And out of that, we have this string theory, and we're just kind of stuck right now. It's not going anywhere either. All right, so physics gets real interesting at that point, but it doesn't make any predictions that we can test or observe at this point. So that's where we're at.